Okay. Your specific questions, or should I open
Um,
up like a homework document or something, or lab?
um, no, it's from the back of the chapter. Question on page 341.
Okay. Uh, okay.
So problem 7 and 9, for both of them, I got the electron configuration, but the back of the book um, has the actual configuration, which is different. And we kind of talked a little bit about this yesterday, I think, about how it's different from expected.
Right. So let's take a look here and see what you should have gotten using the SPDF block, because that's the answer I would expect on an exam.
Oh, good. Okay.
Okay. So let's see what I would get using the SPDF method and compare it to what you got. Okay.
Okay.
So I'm going to do a change share here. And the way they asked this question from the back of the book, it may very well be that they just wanted you to look up the electron configuration in the chapter because they're all listed, and then write it out. Uh, here's what I mean by they're all listed. If we go back a few pages, they're on page 316. 109 electron configurations. So you can check your answer there to see if you got what the book reports as the real electron configuration.
Right.
But it doesn't help you with the SPDF method sometimes.
Okay.
So let's take a look at number 7. We're supposed to look at tantalum. And looking in our book, tantalum is where?
After xenon.
Okay, it's number 73. And the element before it is xenon. So you should get 6s2, and then 1, 2, 3. This is 3D, 4D, 5D. So 5D3. And then you have to rearrange it, and you get xenon, 5D3, 6s2.
What about 4S?
Pardon me? Oh, I'm sorry.
4S.
Yeah, I skipped that. Too
Okay.
early in the morning. 6s2, 5d3, and 4f14. This is what happens when you don't drink your coffee before class. So that's what you should get using the block method. Is that what you got?
Yeah.
Okay, now what page should I say those were on? Like 308 or something?
I don't know.
So tantalum.
That's right.
That's what they give?
Yeah. 73, bottom, second column.
Okay. And the answer in the back of the book is different than this?
No, it's, I guess, B, platinum is different.
Oh, okay. Platinum. So let's do platinum next. PT. So platinum is in the 6th period. So the preceding noble gas is xenon. So we're going to write a 6s2, 1, 2, 3, 4, 5, 6, 7, 8, a 5d8, and a 4f14. And we're going to rearrange this, and we're going to get xenon 4f14, 5d8, and 6s2. Now this might be one of the ones where the 6s2 go away and they become 5d10. So
5d9 and 6s1.
oh, that's what they get?
Yeah, but I don't understand why.
Well, here's something you have to understand about energies. So here's n equal 1, right?
Mhm.
Here's n equal 2. Here's n equal 3. Here's n equal 4. Here's n equal 5. N equals 6. N equals 7. They get really close together right here. So remember the lab where you found out that the energies are really close together for high N?
Yeah.
So if they're close together for high N, what does that mean about the energies of a 5D versus a 6S? When you look at the difference between a 5 and a 6 here.
The change of energy is not that great.
Right. So it's not very unusual for an electron to be in a different subshell than you expect it to be.
Okay.
Because those subshells are very, very similar in energy. So this is what I would expect for the exam.
Good. Okay.
Now, I think we were also supposed to do the, were we supposed to do the orbital box diagram?
No, it just says noble gas and SPDF.
Okay. I really don't like the way they word that. It should be, or did they word it correctly this time? Did they say noble gas SPDF, or did they say SPDF noble gas?
Noble gas and SPDF.
Okay, that's good, because sometimes they do it the other way around and it's backwards. It's not really well written.
Makes it sound like they want both.
Right. And if they do want both, then they should write 2 sentences, give the SPDF notation without the noble gas,
Yeah.
and then give the noble gas and remainder in the SPDF.
So I don't need to be concerned about those minor differences as long as I'm getting.
Right.
Yes.
You're not expected to get the real one if it differs from the model that we use.
Okay.
Now, you said that the real one was 5D9 6S1.
Yeah.
Okay, so in that case, if you think about it, xenon, not xenon, but platinum has 78 electrons, right? Because its atomic number is 78.
Mm-hmm.
So here, only one of the electrons is different than it should be,
Yeah.
right? That's 1 out of 78, which is about 1.5% of them are wrong. So another way to look at this is that this electron configuration is like 98.5% correct. So we shouldn't think that just because it's different than the model, that the real one is different than the model, that the model is insufficient or bad. No model is perfect. So 98.5% for a chemistry model is pretty darn good.
Yeah.
So that's the way to look at this, so that you don't feel defeated, but you feel successful. Okay.
Okay.
Okay. That sounded so fatherly, didn't it?
Yeah. Very insightful.
I'm practicing. Okay. Americium is down here in the moat, as I call it. In the moat. and it's in the bottom of the moat. And the preceding noble gas is xenon.
I thought it was radon.
Well, it is radon.
Okay.
And then when we go over to from radon, we hit period 7, and we're going to put a 7s2.
Mhm.
And then we hit actinium, which is going to be a 3D, 4D, 5D, 6D, 6D1. And then from 89, we're going to drop down to 90 and go across 1, 2, 3, 4, 5, 6. So this is going to be a 4 F6. And, we can double check to make sure that we're looking good by counting up. Radon has 86 electrons, right? Because its number is 86.
Mm-hmm.
And here we have 2 plus 1 plus 6, which is 9. So 86 plus 9 is 95, right?
Yeah.
So we have 95 electrons written here. And if we look at americium, it's got 95 protons and therefore 95 electrons. So at least that part looks good, right?
Yeah.
So when we rearrange this, we get radon 4F6, 6D1, 7S2. We don't even have any 5s in there. Oh,
I think
it's a 5F. It's a 5F4 or 5F6, not a 4F. I made a mistake. So there are some 5s in there. So that kind of caught me off guard because I looked at the 4 and then we jumped to a 6 and a 7, and I thought that was kind of odd.
Yeah.
So that was the hint to me that, oops, I pulled it from the wrong part of the moat. Okay, now this is one where I could easily see the 6D1 becoming an F and this becoming a 5F7. And the reason for that is if it were a 5F7, that would be a very symmetrical orbital. And you don't really need the 6D1. But then again, maybe it doesn't.
That's what the book.
Pardon me?
The book has 5F7, 7S2.
Right. So the 6D gets elevated to a higher energy orbital, right? Because a 5 is more energetic than a 6. But the trade-off is that when you put it in the 5F, it's a more symmetrical arrangement.
Okay.
But you wouldn't need to know that. You would need to be able to get this electron configuration here. Now, something I could throw at you, and I'm going to throw it at you right now, is this right here. So we're going to call this number Tony's question. So Tony's question is, there's an element that has this electron configuration. What element and what configuration using the block method?
Okay.
And then why is it different? So how would you figure out what element this is?
We're going to add up the electrons and I get 102.
Okay, so how many for radon?
86.
Okay, and then here we have 14 plus 86 is 100, right?
Yeah.
And 102, so what element is it?
NO.
You don't want to try and pronounce that?
No.
Are you serious?
But
Let's see, where is it?
bottom right.
So you don't want to try to say nobelium.
Not this morning.
It's just nobelium. Okay, so it's nobelium because nobelium has Z equal to 102, and the configuration has 102 electrons, right? Do you remember that Z is the symbol for atomic number,
Yeah,
which is weird?
yeah. Instead of A.
Okay, so what should you get for nobelium?
With noble gas. Oh, okay.
Yeah, using the block method.
The 7s2 61 5s 13, I think.
Okay, and then when you rearrange it, as you always should,
5s 13 61 7s2.
7s2. Okay, so that's what you should get.
Yeah.
Why are they different?
Mm,
And here I'm going to draw this 5F14 and 7s2. So 5F14 is going to look like this. One per before you pair them. You didn't see me pair them beforehand. That didn't happen. You just think you saw it that way. Okay, so that's this guy, right?
yeah.
This guy is going to look like this. One, two, three, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. And then we're going to have a 6D1. And then we're going to have a 7S2. So which one of these looks more symmetrical? Where, everything looks nice and tidy. This one or this one?
The top.
Yeah. So here, the asymmetry results right here in this unpaired electron. So the way to think about it is all of these electrons, and there are what, 16 of them? They're in a particular amount of space, right?
Mhm.
And these 17 electrons, you want to be as spread out as possible. And the reason you want them to be spread out as is possible is because they repel one another. Okay, can you see that there's a little bit of real estate here that is unused in this electron configuration?
Yeah.
So if that real estate, that part of that orbital is basically unused, that means you're keeping electrons kind of out of there. So that means that the overall amount of real estate that you have to spread those electrons out is less. So what's going to be better, having a larger space to spread out your electrons or a smaller space to spread out your electrons? And the answer is, if you've got 16 electrons, you want a larger space. So that asymmetry represents real estate that's not available for an electron, and therefore the repulsion is not as good as above. That type of argument is only good usually for 1 or 2 electrons, but not for like 3 or 4 or 5.
So this was answering the question why they are different.
Yep. And so what would the words be? The words would be that, well, the real electron configuration is more stable because the electrons can spread out more. That's it. Say it back to me.
The real electron configuration is more stable because it's more symmetrical.
That's not what I said. More symmetrical doesn't
Spread
really
out?
explain it.
Okay.
It's because the electrons can spread out more.
Okay.
Okay. So symmetry is kind of a quick way of saying they can spread out more, but it's not as good as saying that they can spread out more.
Okay.
Okay. So we would write, why is it different? The real is more stable because electrons can spread out more. And that's a great explanation for why that one's better.
Okay.
Okay. Okay, good work. What next?
Number 25.
Okay, so that must be like 341 or something.
342. Manganese. Manganese.
Manganese is found as MnO2 in deep ocean currents. Depict the electron configuration of this element using the noble gas notation. Using the orbital box diagram, show the electrons beyond those of the preceding noble gas for Mn plus 4. Is Mn plus 4 paramagnetic? And how many unpaired electrons does the manganese 4 ion depict? So here, I'm not sure. Hang on a second. I want to read A and B again.
For A, I just did the element, not cation.
Okay, yeah.
Is that
I wish they had written that, if they had thrown the word neutral element, that would have helped, I think.
okay?
So for 25A, we just want manganese.
Okay.
So manganese is right there in period 4. So we're going to go back to period 3 to get the noble gas, which is going to be argon. Then we're going to drop down to period 4 and get 4s2. And then manganese is 1, 2, 3, 4, 5. It's the 5th element over in the 3D block. So 3d5. And then we're going to pigtail this and write argon 3d5 4s2. Okay, but it does ask for the noble gas SPDF, right?
Yeah. And orbital box.
And an orbital box diagram. Okay, so here's the orbital box diagram, argon. There's my 3D, 5 boxes. There's my 4s1 box. 1 electron per box. And then 2 electrons in the 4s. And this is a very symmetrical setup, wouldn't you agree?
Yeah.
Okay. Now for B, what is the manganese 4 plus going to look like? And the way you always get these is you start with a neutral. And since this is a +4, that means you have taken away 4 electrons. That's how you get the +4 charge.
Yeah.
So we have to take away 4 electrons from this configuration. So we're going to start with argon, 3D, and these 4s, 2 of them have to disappear, and these 3D, 2 of them have to disappear. So it becomes 3D3.
Okay.
And of course, the electron, the noble gas orbital box diagram is only going to have 3 electrons in the 3D. And we're not going to bother drawing the 4s and show that it's empty because you don't really draw orbitals that are empty.
Right.
So this is what I would expect for A and B.
Okay.
And let's see, there's a C and a D, right?
Yeah.
C, is it paramagnetic? And it'd be yes. It has 3 unpaired electrons. Now, why don't I worry about argon? How many unpaired electrons are in argon?
None.
None, because every subshell is full.
Yeah.
Okay, D. How many unpaired electrons does, oh, I answered D already. There it is. So I used D as my explanation for C rather than just saying yes.
Okay.
So that's how you do that one.
I'm not sure why I was confused on that one.
Well, did you get these answers that I got?
No. I
Okay.
mean, I guess I was just thrown off with the +4 because I haven't
Okay.
had much practice with the cations and anions.
So you just have to remember that for this to turn into a cation, you can't gain protons because then you would become a different element, right?
Yeah.
So you have to lose electrons, and then you have to think, well, how does losing electrons tie in with the electron configuration? And the answer is you got to take electrons away from it.
Right.
Okay. So we did 7, 9, and 25. What would be next?
26. It's really similar. I think I got it. It's with a cation, 2 of them.
Okay, 26. The question is blah, 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 blah. This is an interesting compound. It looks like a nickel peroxide thing.
Yeah.
The OOH is the peroxide ion. But it's not a peroxide, I can tell now. It's actually a nickel. This is the first time I recall seeing a compound that has 2 anions. How do I know it's got 2 anions? Well, they tell us that the nickel is +3, right?
Yeah, so that's not an anion.
It's not an anion, but we've got O and OH, right? And what does the charge have to add up to for O and OH?
I just see hydroxide.
What's that?
I just see hydroxide.
Well, it says NOOH, right?
Oh, okay. Yeah.
So I agree that has to be hydroxide. But what does that have to be?
Oxygen with a 2-.
So it's got to be an oxide ion. So this is why I'm saying this is like the first compound I recall seeing with 2 different anions. And this makes sense given the formula and given the fact that they tell us it's N+3.
Yeah.
Okay. So they say N+3 is reduced to N+2 or nickel +2. I keep saying N, but it's really nickel, Ni. Using the orbital box diagram and noble gas configurations, show electron configurations of these ions and are either paramagnetic. So the way we're going to do this is we're going to get the electron configuration of nickel first. And nickel is in the 4th period. So the preceding noble gas is going to be argon. And then 4s2. And then nickel is 1, 2, 3, 4, 5, 6, 7, 8. It's 8 over, so it's going to be 3d8. And we're going to do a little switcheroo and call it argon. 3d8, 4s2. Okay?
Okay.
Now for nickel +2, we're going to have argon 3d8. We're going to take away the 4s2.
Oh, okay. I did it wrong.
Okay, so You always take away the electrons after you rearrange it,
Right. It makes sense.
because they're the least stable electrons, and they're the ones you'll take first.
Yeah. So the nickel plus 3 is 3d7.
Now they do want us to do the orbital box diagram. So this would be argon, 3D. And we're going to put 8 electrons in here. So we put the first one into each box individually. And then the last 3, we're going to pair them. And that would be nickel plus 2.
Mhm.
And nickel plus 3 would look very similar, only it would be 3d7. So it would be argon with 7 electrons in the 3D subshell. And these would be your 2 answers. And then are either of them paramagnetic? And the answer is they both are, right?
Yeah.
What is the reason each of these are paramagnetic?
They have unpaired electrons.
There you go.
Okay.
Okay, that's 26. Not bad, not shabby.
So the rest of my questions were about periodic properties or trends.
That's fine. Ask away.
Number 29.
Okay, 29. Select the atom or ion in each pair that has the larger radius. So for A, we're looking at chlorine or chloride or chlorine. And which one is larger? And the answer is
It's the ion, right?
hang on a second. I just want to make sure I'm reading it correctly. Okay, larger radius. So chloride has the larger radius. And our reason is that they both have the same nucleus. But chloride has, let's see, chlorine is element number 17. So chloride has 18 electrons, chlorine only 17 electrons. And do you remember how I said that electrons are pushing each other around?
Mhm.
So 18 electrons are going to push to be a larger radius than 17.
Okay.
And it's significantly larger.
Good.
If you take a look at the periodic trends, so if we look at in our book here, so these are the radii of atoms. And you see that chlorine is 99?
Yeah.
And that is actually the radius. So it's more like 200 across, right?
Yeah.
So that's important to remember. They're giving us the radius. Okay, now here are the ions. And again, if we read this, you see it says radii.
Yeah.
Here's chlorine, and the radius is 181. So it's twice as large as the chlorine atom. They even have the size of the chlorine atom here in light type where it says 99. And so when you look at these light type, I'm going to zoom in on this so we can see it a little bit better. And let me focus here because when I zoom, it doesn't automatically refocus. you can see that, in some cases, the radius is more than double for the ion, right?
Yeah.
Now, the reason we could say that this is more than double is because we're actually adding 3 electrons. So that's more significant, right?
Yeah.
Here you're adding 2 electrons. Here you're only adding 1. But especially for those in period 2, the difference is pretty astonishing. It's more than double. Oh, well, in most cases, it's more than double. Okay. Here also, it's pretty significant, 104, 184. So which of these numbers do you think I want you to memorize?
None of them.
None of them.
Okay, good.
What do you think you should know about the radius of the anion versus the neutral atom?
The anion is larger.
That's correct. That's what you should know. And if we take a look at the cation, can you see how it's the opposite case? So the more bold number is the ion radius, and the less bold, the faded type, is the neutral atom. So which one has more electrons, the neutral atom or the cation?
Neutral.
The neutral atom. So therefore, it should have a larger diameter. And this is the case.
Okay.
So without reserve, without question, always, the cation is smaller than the neutral atom, and the anion is greater in size. And when I say size, not only is that radius, but you could say it's diameter too, because that's the same type of idea. But you could also say volume, right?
Yeah, I guess so.
I mean, look at this. That little grape inside has a volume, and that circle on the outside, if it's a sphere, it has a volume. They are quite different volumes, right? And why do I talk about volume? Well, I talk about volume because when you think about a small volume versus a big volume, it kind of tells you how close things can get together, right?
Yeah.
And bond length. Okay. So we've talked about the ideas that would help us to answer 29A. Let's look at 29B. Okay, 29B is aluminum or oxygen. Okay, so let's look at our periodic table. We don't want to look at the charts that the book gives us to answer these questions.
The chart?
Because, well, yeah, the little charts that show you the different radii.
Yeah.
We don't want to answer it based on that unless you're going to write those charts down in your cheat card, right? So we want to be able to do this without looking at that, but just looking at the periodic table and seeing where they are on the periodic table. So aluminum and oxygen are in different periods, right?
Mm-hmm.
And this is a great way to do atoms like this. Aluminum is neon, 3s2, 3p1. Oxygen is helium, 2s2, 2p4. Okay?
Okay.
So here, the outermost shell, outermost occupied shell, is 3. And here it's 2. And in general, you're going to say that if your outermost occupied shell is a 3 versus a 2, you're going to be bigger. Remember how N also not only tells you the energy, but also gives you an idea of how far away from the nucleus?
Yeah.
So here, we're going to say aluminum is greater than oxygen because the outermost occupied shell is 3 versus 2. So what's OOS stand for?
Outermost occupied shell.
Right, because I don't want to write that whole shtick again.
So is it okay in thinking that the farther down an element is, the larger its ion or atomic radii?
That's your hypothesis?
Yeah.
Well, let's test your hypothesis.
Okay.
So here they are. How does it look for group 1A?
Yeah. Gets
They
larger.
definitely get bigger as you go down. How about for group 2A?
The same.
They definitely get bigger. How about 3A?
Yeah.
One glitch right here, 143 and 122. But for the most part, do they get bigger?
Yeah.
How about group 4A? 4A, there is no glitch.
Okay.
How about 5A? 5A, no glitch. 6A, no glitch. 7A, no glitch. There's only this one glitch in there. So out of how many atoms do we have here? 1, 2, 3, 4, 5, 6 times 5. We've got 30 atoms here, and only 2 of them are weird, right?
Yeah.
So would you say that your hypothesis, it looks pretty good, that the lower down in the periodic table it is, in a group, the bigger it will be?
You're right. Yeah.
I think you should know that. Okay. Just like if we look across a period, look at these radii, 152, 113, 83, 77, 71, 66, except for fluorine, which is a glitch. What happens to the radius?
It's larger on the left and
Uh,
declines to the right.
I would say going across to the right, it gets smaller. But you can say going to the left, it gets larger.
Yeah.
How about here on the third period where we have sodium? You'll notice here that there is no glitch. It works perfectly.
Yeah.
For the fourth period where you have potassium, there is a glitch here where you got 122, 123, and 125. But you would also argue that those are so darn close to one another that it's not a big glitch.
So if we are asked a question like this, should we draw orbital box diagrams to confirm?
No, but you should be able to explain why they get smaller when we go across.
Because they occupy larger L?
No. So has nothing to do with L. Has to do with the nucleus.
More protons and neutrons?
More, well, it has nothing to do with really the neutrons, it's the protons.
Okay.
So it's kind of an obtuse argument, but let's see what C asks us, because maybe that will allow us to talk about this argument. So we have indium or iodine. And let's see, where are they? Okay, so they're both in the same period.
Period 5.
And we have xenon, iodine, tellurium, antimony, tin, and then indium right here. So we're comparing these two guys. So what we should suspect here is that indium is going to be larger and iodine smaller. That's our prediction.
Yeah.
Now, here's why. If you look at indium and you look at the orbital box diagram, which I always like to do because it can help explain things. I'm going to get the SPDF notation first. So the element before indium is krypton. And then going across, we get 5s2, 4d14, and 6s1, right?
Yeah.
And when we rearrange this, we would put the, why did I put 4d14? 4d10, right?
Yeah.
Okay. When we rearrange this, we get krypton, 6s1, 4d10, 5s2, 6s1. And for iodine, we're going to have krypton, 5s2, 4d10, 6s5. And when we rearrange that, we're going to get 4d10, 5s2, 6s5. So what is the outermost occupied shell on both of these? Why do I have 6s5?
I don't know.
That should be P, right?
5p.
5p. I'm all over the place on this problem. Okay, what is the outermost occupied shell on these?
5.
The fifth, right?
Yeah.
Now, why would iodine be smaller than krypton or smaller than indium when it has more electrons? Well, here we have to look at the atomic number. The atomic number of indium is 49. And for iodine, it's 53. So I'm going to go to another piece of paper here. Now, if you have a nucleus with 49 protons in it, and you've got an N equal 5, compared to a nucleus with 53 protons in it, and you've got an N equal 5, which one is going to be able to pull those electrons closer to it because it's got a larger charge? This one.
Right.
So this has a greater attraction for electrons and pulls them closer.
Okay.
And what could we say about that?
That's an explanation for the trend.
Well, what can we say about this guy?
Oh.
Less attraction for electrons, so it's not able to pull the electrons into a tighter radius.
Yeah.
So letter C for 29 allowed us to take a look at that periodic trend in the period, not the group. But in the period, they tend to get smaller because you're sticking the electrons into the same outermost shell, but you're also adding more protons, which pull on that outermost shell better.
Okay.
So that's kind of what's happening here with the atom. You have to think about, you know, before I was focusing on the electrons are pushing each other away, right? Because they repel one another.
Yeah.
But then the counterpoint is, well, what keeps them from just pushing each other away off into infinity?
The protons.
The nucleus, the protons in the nucleus. That's exactly right. So it's kind of like a contrast of forces, the attractive forces and the repulsive forces. And naturally, depending on how many protons you have and how many electrons you have, there's going to be a different balance of those forces, resulting in different radii. Okay? Okay, so that's 29C. We would expect iodine to be smaller. But in this particular case, it may be different, because if you remember the trend in period 2, fluorine actually ended up being bigger than some of the other ones.
Mm-hmm.
So iodine may very well be a little bit bigger than indium here. Our book does not show indium, I believe, so I don't think we can check this, but it might be worth looking to see if it's in there. Nope, it does show it, and indium is 163 and iodine is 133.
Oh. Okay.
So indeed, iodine is smaller. Why?
Because it has less positive attraction from the
No,
smaller amount of protons.
iodine is smaller because it has more protons, pulling the electrons in tighter.
Yeah.
But we also have to say, not only is it pulling those electrons in tighter, the way it can do that is that they're pulling on the same type of electron, so it's able to pull them in tighter.
From the same shell.
Yeah. So we're looking at fifth shell electrons that are just defining the outermost shell. And when you have more protons, it pulls it in tighter. Okay?
Okay.
Okay, what next?
34A asks about the most metallic character. Did we talk about, was that in lecture? Metallic.
We didn't really talk about metallic character, but I think this one is pretty easy to answer.
I would think the metal.
The metal has the most metallic character. That's it.
Okay.
Why do you not pick boron or silicon?
Well, they're metalloids.
Bingo. So 34A, we've got to say aluminum has the most metallic character because it's a metal.
Okay.
So what they're doing with that question is they're probably trying to get you to go back and recall what the metals are, the non-metals and the metalloids.
Yeah.
Okay, what next? Did we deplete your questions?
No, one more. I think 35.
Okay, 35. Explain each answer briefly.
That's what I had kind of trouble with.
Place the following elements in order of increasing ionization energy. So let's look at 35. A, we want increasing ionization energy. So here's what these symbols mean. Arrow up means increasing. E means ionization energy.
Yeah.
So ionization energy is when you take an atom that's in the gas phase and you add energy and you end up getting a cation in the gas phase.
So,
and the electron that comes off, we write down as an electron in the gas phase. And so here the electron has been taken off of the atom completely. So if you have an atom with a nucleus and you have all of these shells, and we're going to take this electron off, it's going to end up looking like this. And here I'm going to put 2 electrons here. This is an example of lithium becoming lithium cation. So that's ionization energy.
So isn't it the amount of energy to remove an electron?
Pardon me?
Is it the amount of energy to remove an electron?
Does this kind of show that this is the amount of energy to remove an electron?
Yeah. So
Okay.
the
So
higher.
this is ionization energy. Okay. But I just want to lay it out in very general terms. And actually, there's more than one ionization energy. There's ionization energy 1, 2, 3, 4, 5. Because you could remove this electron here, then you could remove the second electron, then the third. Lithium has 3 ionization energies, and they get bigger and bigger and bigger. And the reason they get bigger is because when you take away an electron from an atom, the way you think about this is that's the first one. Oh, this should be a 1 plus. That's the second one. And that's the third one. So here, the first one, you're resulting in a +1 and an electron. Second one, you end up with a +2 and an electron. Third one, you end up with a +3 and an electron. Which electron is harder to pull off? And why? What's that?
The one closest to the nucleus.
Well, actually, we don't even need to make that argument. We can just say, well, the charge attraction depends on the size of the charge.
Yeah.
So if you're taking away an electron from a +3 charge, it's going to be harder than an electron from a +1 charge. That's all there is to it.
Yeah.
Okay. And the hardness of these, if that's all that mattered, for these different ionization energies, you'd expect this. This one's that hard. This one's twice as hard. This one's 3 times as hard. That's what you would expect. But you'll find out that they are not like this. They end up being like this. That's the first one. And here's the second one. And here's the third one. So these two, they don't quite line up. And that has to do with the fact that they're in different shells and stuff like that.
Right.
But this is what we would normally expect if all electrons were equal. Okay, so for A, we're supposed to answer, place the following in an increase in ionization energy. So we've got fluorine, oxygen, and sulfur. For these, it really helps to write out the orbital box diagram.
Okay.
So for fluorine, it's going to be helium, 2s2, 2p5. For oxygen, it's going to be helium, 2s2, 2p4. And for sulfur, it's going to be neon, 3s2, and 3p4. Okay, now the reason I write the orbital box diagram is because I'm going to circle the electron that gets taken away. So here, are we going to take a 2s electron or a 2p electron? And the answer is, we're going to take a 2p electron because it is less stable. Now, which one of these 2p electrons are we going to take away? We're going to take away this single one, or we're going to take one of these that's part of the pair? And the answer is you're going to take away a paired one because it's being repelled by the other one. So these are twins in the same room, then they're fighting. It's going to be easier to take one twin out of the room than it is to take a single person out of their room who's just content. So I'm going to circle this guy, and that's a paired 2p electron removed, right?
And wouldn't we remove that one because it was the last one added as well?
Well, we don't really need to talk about whether it's the last one added or not, because that's Hund's rule for how we put them in there. But we're talking about how do we take them out? Remember, Hund's rule is just a model for how we put the electrons in. And it's supposed to be based on stability. So we don't want to simply say, you know what, we're going to take that one away because we're following the reverse of Hund's rule. We want to be able to explain why. So why is that one taken out?
I don't know.
Well, you want to say it's the least stable electron.
Because that's Hund's rule.
That's Hund's. So the impetus of Hund's rule is it's about stability.
Right.
So just saying, oh, it's Hund's rule is not a very good idea. It's kind of like saying the speed limit is 55. Why is it 55? Well, because it says it's 55. What's the real reason for the speed limit?
Safety.
Safety. So we're trying to answer this from that aspect, not just, oh, it's the rule.
Okay.
Okay, so which electron are we going to pull here for oxygen?
That paired 2p.
Now, why are we taking the paired one instead of the unpaired one?
The least stable.
And why is it the least stable?
Because it was the last one added.
No, because it's being pushed out of the orbital by the other electron.
Right. Okay.
Okay. So paired versus unpaired matters. Okay. Now, let's look at this one. What's going to be taken out? This guy, right?
Yeah.
Paired 3p. Now, the other thing that we want to know for each of these is we want to know the atomic number. Really, you want to know the effective nuclear charge, but we don't memorize those things. So we're going to go with atomic number. What's the atomic number of fluorine? It's 9. Oxygen is 8. And sulfur is, I think, 16.
Yeah.
Okay. So here's all the information we need to answer B, or answer A. And we want to go with increasing ionization energy, right?
Mm-hmm.
So that means we want to start with the easiest and go to the hardest. Now, first thing you do is you look at these. And you look at the N. Larger N is easier.
Right.
So we're going to go with sulfur is the easiest because we're removing an electron from larger N, which means it's farther away from the nucleus, easier to take.
Yeah.
Now, what about oxygen and fluorine? They're both in the same shell and they're both paired. Which one's going to be easier to take? Well, then we have to take a look at the nucleus. Who is going to hold on to those electrons better, fluorine or oxygen?
Fluorine.
Fluorine, because it's got more protons, right?
Right.
So oxygen is the middlest to remove. And then I'm going to jump to fluorine is the hardest to remove. And for fluorine, I'm going to say it's the hardest to remove because the electron is removed from the same subshell as oxygen, but fluorine has 9 protons and attracts or we'll say holds the electrons better. So naturally, if it holds the electrons better, it's going to be harder to take.
So first we look at the outermost shell, and then we go to Z.
Then you go to the nucleus.
Yeah. So
Then,
the atomic number.
and then what you may have to do is, let's say that we're looking at sometimes it's a matter of paired versus unpaired.
Yeah. So paired is easier to take because
Yeah.
of the.
So, as far as starting with the shell first, that's the first thing.
Yeah.
But normally you go to paired versus unpaired next, and then you go to the nucleus.
Okay.
We may run into an example like that with B or C. Let's take a look at B, okay? So this is 35B, which has the largest ionization energy, oxygen, sulfur, or selenium. Well, if we take a look at these, we can see that they're in different periods, right? This is period 2. This is period 3, and this is period 4, which means the outermost occupied shell for oxygen is going to be the second period. Sulfur is going to be third. Selenium is going to be the fourth. So you're removing a second period electron versus a third period versus a fourth period. So which one's going to be harder? Oxygen.
Yeah.
Selenium is the easiest, and that means sulfur's the midlist. So if we put these in order, we're going to write from increasing lower to higher. We're going to go selenium is easier than sulfur, is easier than oxygen.
Okay.
Let's take a look at C. Which is the most negative electron attachment? So electron attachment enthalpy, let's talk about that.
Yeah.
Electron attachment enthalpy. So electron attachment enthalpy is the opposite of ionization energy. So if you have an atom in the gas state and you add an electron to it, what will this result in?
A negative charge.
Right, an anion. Now, it turns out that if you have an atom, and here's your nucleus, and here's your shell, and you have an electron come from infinity and end up on the atom, that's going to emit energy, right?
Yeah.
We've seen that with an electron going from n equal 2 to n equal 1. It emits energy when it goes down. And here it's coming from infinity to the electron, so that's going to emit energy. The interesting thing is there are electron attachment enthalpies. There's like for getting 1 electron, for getting 2, for getting 3, and so forth. Only the first one emits energy. And the reason only the first emits energy is because the second one, you're putting on a negatively charged atom. And is that negatively charged atom going to attract a negatively charged electron? So here, this guy is going to absorb energy. In other words, you have to force this anion to take an electron. Okay, it's kind of like I don't know, forcing your a friend to take care of your kid who doesn't want to take care of your kid. You gotta sweeten the pot, right? Well, I'll tell you what, I'll take you out to dinner. Here, this is like asking your mom or dad to take care of your kid because they would just love to, as long as it's for only about an hour or two so they don't have to change a diaper. Okay. Now you think I'm making that up, but that's the way it worked in my family. Only an hour or two.
Yeah.
And make sure you change them before you bring them over. Okay, so here we're going to put plus electron attachment enthalpy. I'm going to put EA. Now, this is going to be a negative value, right?
Right.
Now, there is something else called electron affinity. And electron affinity is basically equal to the electron attachment enthalpy. I'm going to call that EAE, but it's the absolute value of that.
Yeah.
So if this is a negative value, this is a positive value. Okay. So this is why the question says, what has the most negative attachment enthalpy?
Right.
And we're really looking for what is the biggest change in energy. Okay, so what are the things that are going to expect the amount of energy, or expect, what are the things that are going to impact the amount of energy released? So for instance, if we have a nucleus and this is n equal 2, and we have a nucleus and this is n equal 3, so you have an electron drop here or an electron drop here, which one is going to have the more negative electron attachment enthalpy? The first case or the second case?
First.
Right. Is more negative because you're ending up at a more stable position. And here, this is less negative because you're ending up at a less stable position. So the first thing you want to do when you're comparing electron attachment enthalpies is find out what shell it ends up in. The lower the shell, the bigger the release of energy.
Right.
Okay. Now, what else would impact that? Suppose they end up in the same shell. Well, then you have to look at other factors, and usually it's the nucleus. So let's say that this is a +5 and this is a +4. Which one's probably going to release more energy? And let me draw this a little differently. Which one's going to have the smaller radius?
+5.
Okay, so I got to cross this guy off, and I got to put the n equal 2 closer to the nucleus because this has a bigger nucleus, right? So now when I come from infinity, which one is going to have the more negative electron attachment enthalpy? This one that ends up in this 2 or this one that ends up in this 2?
The +5.
You're right. And you can actually see with my drawing that it is a greater amount of energy.
Yeah.
I'm not trying to make it proportional. I'm trying to convince you that because the radius is smaller, it's going to give off more energy. So more, and I hate writing this, but I'm going to do it, more negative electron attachment enthalpy because of the nucleus, right?
Right.
So that's how we're going to approach these problems when we're trying to answer them, okay?
So shell number and nucleus size.
Yeah. So can you see that they're essentially the same reasonings we use for ionization energy?
Yeah.
You just need to know which to apply when.
Okay.
And the answer to that is, well, if the shells are different, apply that one.
Yeah.
And then if they're not different, then you go to the nucleus.
Okay.
Okay, so we're looking at 35B. Oh, C, I'm sorry.
Mm.
And we're looking at selenium, chlorine, or bromine. And when we look at these, we see that selenium and bromine are in the same period. And chlorine is going to be here. So we probably better at least get the electron configurations, right?
Okay.
So for chlorine, if we use the noble gas configuration, we're going to start with argon. And then we're going to have 3s2, 3p5. For bromine, we're going to start with krypton. And we're going to have we're going to have 3d10, 4s2, and 4p5. And this is something you don't want to do. I jumped straight to the rearrange, okay?
Okay.
Don't do that.
Okay.
Selenium is going to be 3d10, 4s2, and then 4p4. So which has the most negative electron affinity energy?
Chlorine.
Chlorine. So we're going to put chlorine here. It's going to be the greatest. And the reason for chlorine here is because the electron ends up in the third shell.
Right.
Okay, what about bromine and selenium?
Well, we have the same shell number.
Same shell number, and it's the same subshell even, right?
So I think it's bromine.
And not only that, but they're both going to be paired when they end up adding in, right? Because there's only one unpaired electron.
Yeah.
Here, there's only one unpaired electron. And so that means, actually, this has two unpaired electrons. I'm sorry.
Yeah.
But the electron ends up being paired. So you can't say one's going to be paired, one's unpaired. So this guy has 17 protons. This guy has 35 protons, and this one has 34 protons. So which is bigger, bromine or selenium?
Bromine.
No, bromine is smaller because it has more protons.
Right. But it has the higher.
So you were answering the question
Yeah.
for the actual question. So here I'm exaggerating it, right?
Yeah.
So here, can you see that an electron starting off at infinity, that this is going to be the more negative electron attachment energy?
Okay.
Because
Yeah.
it's got the larger arrow, right?
Right.
So here we're going to put bromine next, and then we're going to put selenium last. So this particular question allowed us to not only compare, well, what happens if they're in the same period, but what happens if they're in the same group?
Okay.
And then 35D, which has the largest radius? We have O2 minus, F2 minus, and F. The electron configuration is going to help. For these, I often do not use the noble gas configuration. And the reason is this is the noble gas configuration. Does that really save me anything by writing helium instead of 1s2?
No.
In fact, I have to write one more character, right? Because here I'm only writing 1s2, 3 characters. Here I'm writing 4. So I think the noble gas configuration for things in the second period is kind of a waste of time. Okay, so here's the electron configurations. What did we say about anions compared to their neutral atoms?
They're larger.
Okay, so if we're going to go from largest radius to smallest, we're going to say that either fluorine or oxygen is going to be smaller because F2 minus is definitely bigger. That's supposed to be F minus 1, I'm sorry. Because F minus 1 is definitely bigger than fluorine, right?
Yeah.
So we're going to say this is a fact. F minus is bigger than fluorine. Well, let's compare the two anions. What about O2 minus or F1 minus? Well, we're going to say, you know what? Probably O2 minus is going to be bigger, right?
Need to look at the nucleus.
Not so much the nucleus. We're just going to look at actually, now that I think of it, we better look at the nucleus. This guy has 8 protons, this guy has 9, and this guy has 9, right?
Yeah.
So which of these is going to be smaller and why?
Fluorine.
Fluoride
Fluoride.
is going to be smaller than O2 minus, like I was saying down here, but what's the explanation?
Because it has a stronger attraction due to more protons.
Yeah. And here, when we're comparing O2 minus and F minus 1, it seems like we're comparing apples and oranges, but look at how many electrons each has.
Right, the same.
Exactly 10. So when they have exactly the same number of electrons, 9 has got to pull them in better. So F minus has got to be smaller than O2 minus. Okay, so here we can put O2 minus right here, and we've completed our trend. And we can actually check our answer, can't we?
Yeah, I guess.
So here we can see that F minus is 133, F is 71, and O2 minus is 140. So without knowing those numbers, did we put them in the correct order?
Yeah.
Booyah. So you're understanding that when we're looking at these things, you've got to apply the right reasoning at the right time. Sometimes it's going to be shell number. Sometimes it's going to be number of neutrons in the nucleus. And then at other times it's going to be, you know, how many electrons are on that sucker, because more electrons means a bigger thing, right? 9 and 9. Here you've got 10 electrons, here you've got 9. So the one with 10 electrons should be bigger because it's got more electrons.
Will we be needing to explain these on the exam?
Yeah, I might ask for explanations.
Like a brief explanation?
Yes, a brief explanation. And usually your explanation is not going to be because of Hund's rule.
I can't just write Hund's rule.
What would I expect instead of Hund's rule?
The least stable electron.
Yeah, you would say that it's more stable or less stable because, you know, you would say, well, maybe it's more stable because there's more protons in the nucleus.
Right.
Or you'd say it's less stable because there's fewer protons in the nucleus. Or you might say it's less stable because it ends up in the third shell instead of the second.
Okay.
So I want you to understand the root reasoning, which is about stability, not about some guy's rule.
Yeah.
Okay? That's where it's at. And when you understand the guiding nature of stability, it helps you to understand a lot of this better rather than just ticking off rules.
Yeah.
Okay?
All
Well, we've been
right.
at this for an hour and a half, so we're going to call it quits now. I hope you have a nice rest of your day. It's very beautiful here in Eureka.
Yeah. You too. Thank you.
All right. Always good to hear from you. Bye-bye.
Bye.